Okay, so we've made it to the 1913 Nobel Prize in Physics, which was won by this gentleman. Before we get to him, if you haven't yet, click subscribe on the channel and click like on the video. It really does help us out with the algorithm so more people see the content. But the 1913 prize was won by this gentleman, Heike Kamerlingh Onnes. Now, I have no idea if I'm pronouncing that correctly, but I think I'm pretty close. But before we get to a lot of other things about this guy, who did win the prize for investigating materials at very, very cold temperature, and he was the first person to actually liquefy helium. So that was important because it gives you a chance to study these materials at different temperatures. And liquefying helium is difficult today. It takes a process that's just bizarre, and we'll get to that. But he did it in 1908, which was a truly astounding feat. But before we get to all that, there's a few things about this guy you need to know. While he was a student at university in the 1870s, he studied under some fairly notable people. This is one of the two. His name is Gustav Kirchhoff. And to people who may not be a scientist or an engineers, that may not ring a bell to you. But if you are a scientist or engineer, you've studied this guy's work in some way because it is still used today. Remember, he was a professor in the 1870s, and for his work to still have impact today, it's amazing. He gave us Kirchhoff's circuit laws of thermal radiation, laws of spectroscopy, laws of thermal chemistry, a whole bunch of things that students as undergraduates in their first, second, or third years are still running into, and in some places not so happy that they have to study them because they can get a little complex. But this was one of two notable professors he had. Now let's get to the other one. This was his other notable professor, who, I'll tell you his name in a second, but he investigated things like emission spectra of heated elements. He discovered cesium, rubidium. He did a whole lot of things in the lab that people still use and still talk about today. He is so prolific. As soon as I show you the next picture, I guarantee you're going to know who this guy is. That's right. His name is Robert Bunsen. He gave us the Bunsen burner that students in labs all over the world and research scientists, depending on their project, still use in one form or another today. So he studied under two people who gave us things that have not gone away even 150 years later. Pretty interesting set of faculty members. If you're thinking, hey, wait a minute, Dr. Imholt, we've seen this guy before. Well, you have. This is Peter Zeeman, who actually got his doctoral degree under the 1913 Nobel laureate, even though he won the prize in 1902. So he actually won the prize a full 11 years before the guy who he learned how to be a physicist under, which I think is kind of cool because it gives us a chance to see that these guys don't just leave a legacy in technology. They don't just leave a legacy in scientific knowledge. They train other people in their profession. And here's a guy who trained somebody else so well that he won the prize 11 years after his own student did. Now, interestingly, I've actually met a physicist when I was working in New England, who's a professor at MIT named John Joannopoulos, who actually has had two students go on to win the Nobel Prize, and he does not have one, which is a little annoying to him, but he's very proud to have put his mark in the scientific field that handily, where he's got two ex-students who have Nobel Prizes of their own. But here's a guy who was just around the scene of the crime on all kinds of stuff. Fantastic stuff. Now let's look at what his work actually was. This picture, which dates from 1909, shows our 1913 Nobel Prize winner, Onnes, standing right next to the 1910 Nobel laureate, van der Waals, showing him his equipment that he was using to liquefy helium. Now, liquefy helium, or what does that mean? Who cares, right? You can liquefy anything. You can liquefy oxygen, you can liquefy nitrogen, you liquefy all kinds of things. But they turn into liquids at different temperatures. Just like you can get water vapor and it turns into a liquid at normal room temperatures, actually significantly above that, doesn't boil to 212 degrees Fahrenheit, 100 degrees centigrade. Helium's a different critter, right? It doesn't get cold. It doesn't get it to be a liquid until it gets really like crazy super cold, which to the scientific world is 4.2 Kelvin, which is very near absolute zero. But what does that mean in English? It's negative 269 degrees centigrade. That's freaking cold. That's not like, oh, let's just go take it to the Arctic and see what happens. No, you have to set very special circumstances to get this stuff to liquefy. So what he was doing was building these advanced apparatus to turn things into liquids. But guess what he was using? Remember that ideal gas law from one of the other Nobel Prizes we'd already talked about? That's what he was using in all that complicated stuff you see behind him. That was his actual lab. He was playing with pressures and temperatures and all kinds of things to try to mess around with it until you can get it into its liquefied state, which he eventually did. Now, what is that used for? Well, it's used for a whole lot of things in the scientific world, so we can kind of understand how things behave at different temperatures. And that's why, where do things melt at? What are they semiconductors at? What are they conductors at? All that matters when you're designing electronics. It also matters in a few other cases. So in the official prize, he won it for the work on liquefied helium, but he also did something else before he won the prize. He was using that liquid helium to run experiments, and he discovered something that the world would love to find one and design one that works at normal room temperature. It's something that's still going on today. Now, we're not talking about nuclear fusion and cold fusion. That's not it at all. This is a little bit more interesting and far more likely than cold fusion is. Let's take a quick look. As I said, he started using that liquid helium to study other materials as they got colder and colder. So one of the things he was doing was looking at the electrical conductivity of pure metals, such as mercury, like you see here. He also did tin and lead at very, very, very low temperatures. And some scientists at the time, including Lord Kelvin, believed that electron flow through a conductor would come to just a complete stop. You wouldn't be able to send electrons down a wire if it got too cold. And what he found was something else completely and kind of surprising, was that as you go down in temperature, you can get materials to go into what's called a superconductive state. And what that means is there's no electrical resistance as you send electricity down a wire from one spot to another. Now, when electricity comes to our house through the wires from the power station, those wires can get pretty hot. Well, what that is the resistance in those wires causing some challenges of sending electrons down that wire, and that turns into heat. You get some resistive loss. Well, if you could get a superconductor to work at normal temperatures, even normal on a hot Texas summer day, what you could do is produce a lot less electricity to send electricity to everybody's house. So that's why people look for wires with the best conductivity possible to run the wires through your house, copper, other things like that, which are all very good conductors. But if you could get one to be a superconductor, and you could get it to be a superconductor and you don't have to have it at liquid helium temperatures, that would really be something for the world. And that is something that a lot of labs are even working on still today. They don't look at pure materials. All the pure materials have been looked at and said, okay, where does the conductivity change? All that's really well known and mapped out. But now what they're doing is looking at various molecules and different hybrids and different mixes of things and saying, can we get to superconductors at higher and higher temperatures? Or can we get close to that superconductive state? Because if you could do that, the world's the necessary amount of electricity that has to be produced around the world goes very far down, because with no resistance to stop electron flow, no conversion to heat, you can generate less electricity, and you don't have any loss in the lines as you send it to different places. That also means you can generate the electricity and deliver the electricity much further apart from one another, and you don't have to have power plants near where you want to consume that power. So that work is still going on today. That was the Nobel Prize. I think that was probably more dependent on sort of cutting edge technology of the day than anything else we talked about so far. But this one, to me, this one was a really cool prize, because yes, they awarded it for his work in liquefying helium, but I think they awarded it also for his work in superconductivity, because without that liquid helium work, we would have never discovered superconductivity. At least we would not have discovered it at the time frame we did, and we would not be nearly as far along with it as we are today. So that's our 1913 prize. We'll see everybody on the next one. Don't forget to click subscribe, click that like button. We'll talk to everybody soon.